Hello and welcome everybody. We are the Short Circuit Finder Group and we will be presenting our findings and the final version of our product today. I am Matthew Duncan, team leader. So this is David Austin and that's Michael Dugas. We quickly like to thank our advisors and people who have helped us through the project. Don Foster, Dr. Ben Weil, Dr. McCullough, Dr. Costa, Fernanda for administrative, and Matthew Curtis for a little bit of PowerPoint. And so AFC, our sponsor, has an issue where when they find a short circuit, they detect it by checking continuity and then they half the cable over and over until it's found in a small piece of cable. And clearly this is an extremely large waste of time and money. So they're looking for a better way to reduce their time and save a lot more money. So the objective of ours is clearly to design a better way that will do it efficiently and minimize the amount of loss in the cable. So this is the second time that the project has been taken up, and the first group found that thermal detection after connecting high voltage to the cable would create an arc from the cables to the metal sheet. And that arc would create a hotspot which is detectable by thermal sensors. So we're continuing the work with thermal sensors. They tested many other ways but found that this was the most effective. So this is just an image of where it was finally left off for us to pick up. You can see that each side of the machine, there's 4 of them on top, has 10 thermal sensors on each one, and we'll be going more into depth about how we use them later on. So once we had the project and figured out what the past had done, we first had to talk to our customer and figure out what requirements they wanted to continue the project. So this is just the customer requirement matrix, but it's detailed a little bit better here. They wanted to be able to accurately detect a hotspot on armored cable while it's stationary, and then they need to be able to detect it before it cools down on either a 1,000-foot or a 2,000-foot spool. And then obviously they need a way to mark the hotspot so that they can do something with it later on, either mark it with paint or stop their spooling machine or something like that. So once we had our customer requirements done, we broke them down into finer details for engineering. And this is our engineering matrix, which is continued again, and it's broken down a little bit better for you to see here. So we figured out that a good requirement would be that it needs to detect at least 5 degrees Fahrenheit above ambient temperature. And this is based on the sensors. Every time it detects, it needs to output a TTL signal, which is just something to mark the cable basically. And then it must detect within 1 linear foot away from the hotspot. And then it must detect the hotspot while moving at 1.69 meters per second. And this was because the previous team found that it cooled down in 5 minutes. And so about a 2,000-foot spool, that's about how long it would take for it would cool down and not be detectable. And then we also had to use the previous team's equipment. As you can see, it's still used right here. Their sensors and their frame. So we only have a few constraints that are based off the requirements, and it's mostly just that we had to reutilize the stuff from the previous team. Clearly that's a giant constraint because it constrained us to our design. And then we had to still maintain the hotspot in software. So from our engineering requirements, we determined the best way to do it, and you'll see our alternatives later on, was to take 4 sensors, the 4 here, all the way around, and average them together with an op-amp summing circuit, bring it into a microcontroller, and then, as you can see, we've added the LED strip for visual display, and then every time an output has been detected, it will output a TTL signal. So I'm going to have Dave do alternatives now.
So for our project, there are 2 subsystems that we considered alternatives for. The first subsystem being the microcontroller, and we had 2 choices, either the Atmega 2560 or the Feather 8-a-Lauder. With the Feather 8-a-Lauder, it had a much greater processor at 48 megahertz compared to 16 megahertz. Although the Atmega had a lot more digital analog pins, which were used for the ADC conversion, and it was non-volatile, so we were able to unplug it and the program would still be on it. The second subsystem was the sensor setup, and we had 3 different choices for this. The first being the 10 groups of 4 sensors, and for this, For this one, we would have one sensor from each side of the array, and there'd be 10 arrays in total. And in order to evaluate these, we would have a multiplexer or a summing circuit using op amps. For the second choice, we would have 4 groups of 10 sensors, and this would basically use all 10 sensors on each side of the frame. And in order to evaluate these outputs, we would have to use external ECE with a multiplexer. And for the final choice, they'd be using 40 sensors individually, which is how the last team did it. And there would be a master-slave setup utilizing 3 slave microcontrollers and 1 master. So the decisions that we made for both the sensor setup and the microcontroller are as follows. The Atmega 2560 was selected over the Feather 8 Allottor, and the 10 groups of 4 sensors using the summing op amps was also used. And on the left, you'll see a diagram that shows how the sensors interact with the system and the outputs that follow. And then the reasons for these alternatives: for the microcontroller, the Atmega 2560 was selected due to it meeting the speed requirement that was set for us. At the time, we weren't sure if the speed would be a hindrance on the microcontroller or the sensors due to it having a 20 millisecond delay, and also because it contained more analog as well as digital pins. And in terms of the 10x4 sensors that are average, this setup allowed us to have the best 3D image of the cable, as well as the most efficiently mapped to the LED strip, the most cost-effective, and had 10 analog outputs. And on the screen, you'll see a thermal image showing the cable on the top and underside. And basically what this proves is a single point of contact utilizing heat. For our purposes, we used a soldering iron, and you'll see how the heat distribution is shown. And this is important because if there was an arc in the cable, it would also have a single point of contact, ideally, depending on the amount of short circuits that are contained. And here you'll see the summing circuit, a technical design of it. So basically what happens is the op amp has 4 sensors, each of which has a 10K resistor on the other side. And when it's averaged, 1/4 of each sensor is taken and has a gain of 1. And from the data sheet of the sensors, there's a conversion between the voltage to a temperature. When the sensors output, there's an ADC reading, which is an analog digital conversion, and this is between 0 to 1024. From there, it converts to a voltage, and then you can convert that to a temperature. And to have a better understanding of how the boards were laid out, the first board that we used was a shield, and with a shield, it plugs directly into a microcontroller. You just have to change the layout. And you'll see where the pins plug into the board, it lines up directly, and you have the 8 ribbon cables, as well as power and ground connections for all the ribbon cable boards, as well as the LEDs. On this slide, you'll see the ribbon cable boards, and you'll notice that it's identical on either side. This is because for the 10 sensors to properly fit, we have 5 on the left and 5 on the right plug in, and then there's 2 ribbon cables that connect to the microcontroller below. And to have a better understanding of where these boards actually fit into the project, in red you'll see the microcontroller with the shield board connected, as well as the power supply next to it. And for the ribbon cable boards, the picture only shows really 2 in the frame, but there's 4, and each one has 10 sensors connected to it. And then to really understand how big our project is, at least once it would be taken over by AFC, we built a speed test instrument in order to meet the speed requirements, as well as really test having a hotspot go through the system. And here you'll see the actual built speed test instrument and how the cable sits on the 2 bike wheels. It's sent around the system after we heat it up, and the motor can be controlled to reach that speed as well as to get up to it. And I'll hand this off to Mike to finish off the project.
So here's our verification matrix. This is pretty much what we use to test the actual project and to verify that it did meet the 5-degree Fahrenheit detection. Here's an actual example of the test plan that we used. I'm not going to get into detail on that, but there were a lot of tests that we went over. So the condensed version of our test plan was that we were able to measure the 5-degree Fahrenheit temperature change with the machine. We were able to analyze the readings from the sensors. Then we were heat the cable to 200 degrees and speed it up to 1.69 meters per second per the specification, and then review the sensor outputs on the serial monitor. So the test summary, here it is laid out. Number one was the 5-degree difference. You can see it passed, and then it went on to the TTL, which passed. I'm not going to really get into detail on all of these, but every test case that we went through did end up passing. So the summary is that it did detect the 5 degrees, and it worked to our standards. However, the sensors don't accurately detect the actual temperature of the cable. That is because of the aluminum material and the fact that it actually is more reflective. The sensors aren't able to pick up the actual temperature, but it is able to test the change in temperature from ambient. Also, they don't precisely read it because we analyzed that it's too far from the cable itself because we were inherited this mechanical frame. If we were to redo it, we would bring the sensors in closer, only because of the conical nature of their field of view. So here's our schedule. Really what took us the most time was actually planning out the PCB board, which we went over on 31 hours, and then actually wiring it all up took us the most amount of time. Lessons learned. First of all, when you start a design, you need to go over the best case and worst case scenarios. So we inherited all of these sensors, and from the beginning we realized that it wasn't the best sensor choice from the last team. So we had to work with what we were given. But if we were to do it ourselves, we would have spent more time planning and researching the sensors and picked a better case. Also, while ordering parts, there was one overlooked thing, so we had to go back through the ordering process and reorder the part again. So that was a lesson that we learned. Time is money, and when it gets up to actually putting the system together, you want to make sure you have all your parts with you. And then during the design, when we were actually laying out the PCB, there was one connection that we actually did miss. So we learned that it's very important to take time and design it correctly and go through it multiple times, have a lot of eyes on it, because once the boards come in, there isn't much time to change things around. So here I have a video, just a walkthrough of the system itself. Here's the main board. On the bottom of the machine here, you can see the averaging circuits in the middle, 4 ribbons coming off, ribbon cables coming off each side. That's the power supply, 6 amps, 5 volts. Here's the ribbon boards. They connect the sensor cables to the ribbon cable. The overall machine, which you see in front of you, and then the cable, how it's actually fed through the 10 arrays of sensors. And here's an AC motor we use to power the testing rig to get 1.69 meters per second. So here's a video of it actually working. The reason we have it dark is because this LED, although it's very bright to your eyes, it isn't picked up well on video. So you're going to see a slow motion video of a hotspot on the cable actually passing through the machine at 1.69 meters per second. And you're going to see on either side of the red hotspot, you're going to see yellow and orange, which is a little bit less intense than the center spot itself. And I'm going to hand it over to Matt.
So this is our actual results. The left is going to be the ADC values that come out of each of the sensors, and then on the right it's going to show the TTL signal and whether or not it was outputted when it detects it on the left. So just for reference, it's going to auto scale it. So currently it looks like there's a lot of noise, but it's actually only about like 6 ADC or something. So it's actually really noiseless. So it's going to go, and then the peaks come in, and then on the left or on the right, you can see that the TTL signal is actually outputting And for demonstration purposes, there's a light there as well, but we won't be demonstrating it for you right now. And then, just in summary, just some more of the things. We adapted the frame that was given to us, like was asked, and we averaged 10 arrays of 4 sensors to be able to create the final product that you see in front of you. And then we fabricated the PCBs to be able to neaten wiring, and we found that during prototyping there was a lot of noise and a lot of missed ground, so it really just like makes sure that everything is perfectly grounded and in the most noiseless environment possible. And then for future work, for the issues of the sensors and not being close enough to the cable, we would suggest that potentially a machine is produced that maybe like you put in the diameter of the cable and it pulls in the sensors, and then if you have a larger cable, it pushes back out the sensors so that you can get the closest possible reading. And then obviously, when we do it with our machine, the cable bounces up and down. As you saw in the video, it was like red and then like yellow as it bounced through. That's because we didn't have the greatest setup, but their reel-to-reel system shouldn't have any. It should just be a straight line. And then we also could add adjustable knobs that were suggested early on, but we didn't have enough time for, to change the value of when a hotspot is actually detected in the code. We just didn't get around to it, we didn't have enough time, but it is actually a really good addition to the project so that anyone can change when a hotspot is detected. And then the noise that you saw of the 680C could be reduced by decoupling capacitors or oversampling in code, in software, and that's all that we can think of for future work at this point. So at this point, that's the end of our presentation. We'd like to open it up to questions from anybody that happens to have any.